Well, first of all, I'd like to thank you guys for staying and listening today and for the opportunity to come out here and speak. As I mentioned, this is some work that we're doing as a part of NCHRP 9-58. So I'm just going to talk just very briefly about what's going on that project and then focus in on this dosage selection method for recycling agents for high RAP-RAS mixes. It seems to me, based on our Phase 1 literature survey and literature results and survey of the DOTs, that we don't really know how to select the recycling agent dosage that would be appropriate for these high RAP-RAS mixes. And so that's like one of the main products that's going to come out of this project. So I'll focus in on that in terms of what materials we've been looking at, how we're tying to the field, what laboratory tests we're utilizing, and how we're trying to look at the results in a comprehensive manner with binder results, mortar results, and mixture results. And then I'll go on in terms of what we're doing next. So this is definitely a work in progress. This is a giant team. These are all the cats I have to herd on this project. It's a good team. We work well together. We have 2 other universities, and Gail King is our consultant. And of course, we have a lot of people at TTI, including some old guys who help us get the field projects, which is really, I think, has been part of the success of some of our recent national projects. And it's not easy to do. And we also appreciate all of the help from contractors and material suppliers and asphalt pavement associations. And it's a whole big team effort. So I think we all know the benefits of why we're trying to put more RAP and RAS into our mixtures and get high recycled binder ratios. As Buzz said earlier today, it is important to delineate the RAP binder ratio from the RAS binder ratio, because I definitely believe, as others have said, that you're getting a lot of the RAP binder to participate, but I don't think you're getting a whole lot of the RAS binder to participate. And I don't know if you want the RAS binder to participate because it's so ridiculously stiff. So, of course, we're trying to do this to be green, right? Be a green technology, and make sure that we're doing the best we can in conserving our natural resources, and try to use a little bit less virgin materials. But we still are left with some engineering concerns, mainly the stiffness and embrittlement, and therefore the cracking resistance of the mixture. And so that's why we're looking at this from not only a binder perspective, but also a mixture performance perspective. As I mentioned, one thing that we can do to help these high RAP-RAS mixes is we can add recycling agents. We just got to figure out how much do we add. So one mitigation method for some of those engineering concerns is, from an engineering point of view, adding in the recycling agent is definitely going to help us. It's going to reduce the stiffness. It's going to help us with any compactability issues, and it's going to improve the cracking resistance. However, we have to sort of make sure that we don't go too far the other way and have a rutting or a moisture susceptibility problem. And a big thing, I think, that everybody wants to know is how does all this mess mix together, and how are the materials compatible or not. So we got virgin binder, we got recycled binder from RAP, we got recycled binder from RAS. And now we're going to add in a recycling agent. And I'm not even talking about if it's a warm mix, then we might have some other additive in there. We might. We also, even if we put these recycling agents in there, great, it kind of works at least initially, but we don't really know what happens with time. So we don't know sort of the evolution of how these recycling agents might affect these mixtures. So aging is important. We also want to make sure that we're not just softening, but we're also reducing the embrittlement of these mixtures. So not just a softener, not just a softening agent, but a rejuvenator that at least partially restores the phase angle of the binder, not just reduces the stiffness. Okay, so NCHRP 9-58 is a big project over multiple years, 41 months, and we're trying to assess the effectiveness of the recycling agent to at least partially restore the blended binder rheology and improve the mixture cracking performance at optimum dosage rates. So we have to have a way to figure out what the dosage is for the recycling agent to put it into the mixtures that we're going to look at. Then we also, as I mentioned, the evolution of the effectiveness is important. So we need to look at these binders and mixtures with aging. And then at the end, of course, we need to recommend some useful tools, one of which is going to be what I'm going to talk about today. This is just the overall scope. We finished phase 1 last year about this time. and wrote an interim report and had a panel meeting. We did a literature review and a survey. We designed the lab experiment. Right now, we're finishing up phase 2, which is the laboratory experiments. And we're designing the field experiment. These two are kind of tied a little bit. I'll mention that in just a minute. We're writing the second interim report, and we'll have a panel meeting with a few of you guys in the room here by the end of the spring. Then phase 3 is to kind of validate the tools that we come up with in phase 2 with additional field projects, and I'll talk about that a little bit. And the whole thing should be over in 2017, late 2017. As I mentioned, it's hard to get field projects, but it's a really critical part, I think, of what we do in research. So right now, we have a field project in Texas that was built in June of 2014. It's at 0.3 RBR, and it has a tall oil in it. So we're trying to look at sort of the newer, greener tall oil recycling agents compared to the more traditional aromatic type extracts for recycling agents. And that's the focus. We also have a paraffinic and a reob in some of our work, but not what I'm presenting today. But we're focusing mainly on the tall oils and the aromatic extracts. Then we have a field project in Nevada that was built in, thank you. Can somebody shut the door? Thanks. The Nevada field project was built in September of 2015. It also has a 0.3 RBR. It's all RAP. The Texas one is a mix of RAP and RAS. But in Nevada, we have two sections. We have a tall oil and an aromatic extract. So we have both, and we have them both at the same dosages. So we're going to be able to look at really just the effect of the recycling agent type. Then we have we have one also in Indiana, built in September of 2015. It has higher RBRs, 0.4 and 0.5, and it's looking at a tall oil. Then those are the three that we have for sure. Then we're primarily using the Texas field project in phase 2 and a little bit the Nevada field project in phase 2, and I'll show you that. So those are the two I'm going to focus on. The other 4 that you see here, Florida, Missouri, maybe one up in this area, Wisconsin or Michigan, and maybe in New York. Those are sort of all just potential field projects, and hopefully we'll get at least one of those to happen. We've found that you sort of bat about 50% about. I mean, things go crazy, right? So it's hard to get these field projects. So we'll probably get at least one more of those. Probably the Missouri one is what we're hoping. Okay. So as I mentioned, in phase 2, we focused on the Texas materials that were in the field project, and then what we called expanded. So in Texas, they used a PG 64-22. The climate would call for a 70-22. So there's what we call a virgin section that's 70-22 with nothing else in it. Then we have a control section that has 64-22 plus 0.1 RAP BR, and 0.2 manufactured waste RAS RBR. And no recycling agent. And then there's a third section, that's the control section. Then there's a third section where we actually add the tall oil. So the tall oil was added at around almost 3%. Then from that, we expanded, we took these materials and then we expanded on those and we looked at 0.4 RBRs with RAP only and a 0.5 RBR that has a balance of RAP and RAS, so 0.25 from each of them. We also looked at using an aromatic extract. We also looked at using a 64-28. So this is an S-control binder from New Hampshire. So again, using it with the same materials from Texas. And we also looked at with the 64-28P, so it's a polymer modified binder from Nevada. So we changed the virgin binder grade 3 different ways. And then we also looked at using the other type of RAS, which is the tear-off shingles that were from Texas. The Nevada project uses a 64-28P on both the virgin and the control mixtures. And they had 0.3 RAP, only RAP, 0.3 RBR. And we used 2% for both the tall oil, this is wrong, for both the tall oil and the aromatic extract. That's wrong. Sorry about that. So the laboratory tests that we're running, of course, we're trying to determine the PG grade. So we're using the DSR and the BBR. We're also using the DSR to get the Glover row parameter that is just it's at a different temperature and frequency. It's at a specific temperature and frequency, but basically just using G star and delta and calculating a parameter that's been tied to cracking and durability problems in the field. Then in the lab for mixtures, we've been looking at resilient modulus at both 4 and 25C, and we've been looking at dynamic modulus, And then we've also done some fatigue resistance tests with S-VECD. Joe Daniel's been doing those at University of New Hampshire. We're also doing SCB based on 957 recommendations. I'm not going to show that today. And we're also looking at UT-SST, which is a low temperature cracking test that Ellie Hodge has been doing at UNR. It's just the next evolution of the TSRST. Okay, so what we've come up with so far, I'm just going to step through this. This is the overview, and then we'll go into each of these boxes one by one. So first we have select materials, prepare the materials in the different blends, conduct the laboratory tests, and select a preliminary dosage for the recycling agent. Then verify that dosage with some additional binder tests using the Glover-Rowe parameter and possibly FTIR, carbonyl area growth, so to look at the parameters with aging, and then verify the dosage with some mixture tests. So that's kind of the overview of what we've come up with. So the first thing to do is select that target or environmentally required PG grade, like in Texas, that's 70-22. And then if the state DOT wants to, they bump down sometimes that high temperature grade when they add in recycled materials. That's the control binder grade. Figure out what RAP and RAS sources you're going to use, which recycling agent you're interested in, and then figure out what the recycled binder ratios are, again, separating out that from RAP and RAS. Then, this is the hard part, extract and recover the binder from the RAP and the RAS. This is the part that takes forever, and lots of undergrad students work on this in our lab every day. Then we prepare the control blends that have no recycling agent and the recycled blends that have different dosages of the recycling agent. So, for example, with the tall oils and the aromatic extracts, we did usually 0, so nothing, so that's the control, 2 and 10%, so something like that. That's what we've looked at so far. Then you conduct the test. Basically, you're just using AASHTO M320 to get the high temperature grade and the low temperature grade of the virgin or target binder, of the control binder with no recycling agent, and then at the 2 different dosage levels. We have a selected optimum. Now we think it's important that maybe we should look at the evolution of how that recycling agent will be with aging. And of course, we did measure the low temperature properties after rolling thin film and PAV aging. So there is some aging in there. So what we've decided to do now is to take that optimum blend, so it would be at, what was it, 11.5% for that last one that we looked at, and age the binder, that should be enough, and look at the standard that we actually utilized when we characterized the binder, and then also go out to PAV 40 hours. So people are thinking that might be a good way to characterize what happens in the aging rate, what happens between here and here. Measure that Glover-Rowe parameter using a DSR and possibly look at the carbonyl area and how it's changing, what the aging rate, how it's changing. We do have some thresholds for the Glover-Rowe parameter that are based on some tie to field performance. It's not real robust, I would say, but we do have some numbers to look at for Glover-Rowe parameters. But we don't really have an idea of a threshold for carbonyl area, but maybe we would set a rate at which that we're not happy about the carbonyl area increasing. So I don't really know what the thresholds would be here, but is it okay? Yes, then we go on to the mixture verification. If not, then we got to start over with a different mix of material. The last step would be to look at the mixture itself. So we prepare the mixtures at, again, that selected optimum dosage, and we would look at something called coatability index. What we found is that when we got to be about 5.5% recycling agent, and what we found in the literature is that anywhere from about 0 to 2%, people would just adding the recycling agent into the mix, right? Just adding it. From 2 to 5%, they would actually be replacing the virgin binder. So that's what we were doing. These are all by replacement. So at 5.5%, though, we were noticing that on some of the coarse aggregates, we weren't getting good coatability. So what we decided to do is, okay, let's look at, should we do a mix of addition and replacement? Maybe not just all addition or all replacement, but maybe do a mix of addition and replacement. So what we did is we went to another project, back and look at our dosage selection methodologies and some of the factors that we're looking at there. I mentioned that we have high delta TCs. I don't know exactly where that's going to go right now. And we feel it's important to restore that low temperature grade and then try to maintain that while still restoring the high temperature grade. You can't see this too well. I'm going to show some graphs. But one thing to note is the 64-22 Texas binder had delta TC values that were relatively high, 7, 8, 9, 9, 9, and 10, compared to using sort of a more premium S-controlled 64-28 or even a 64-28P polymer modified binder. So when we use the 64-28 unmodified, we get our delta TCs down 4, 5, 7. And when we go to the polymer modified at the same grade, we get our delta TCs to 3 and 2. So we're getting now down below that 5 threshold that other people are talking about for good cracking resistance. So I think that's important to note, that the virgin binder type plays a big role. Okay, and then we also need to further explore the aging effects. All right, so this is back to that virgin binder type. And what we see here is that this is for the 0.4 RBRs in red. This is only RAP. And this is the 0.5 RBRs with RAP and RAS. And so you can see the differences in delta TC are shown by the dots. And so what you see here is that even though the dosages are pretty much the same across the 3 virgin binder types, the delta TCs are lower for the 64-28 binders. Here with the 64-22, when you use the 64-28, you get a big drop actually in the dosage required, at least for this aromatic extract, and you get a big drop in the delta TC both. If we want to look at the recycling agent type, so this is for the same mixture but just taking a tall oil or an aromatic extract. In all cases, the aromatic extract took a little bit higher dosage. That's just the nature of what's going on there chemically. But what you also notice is that in all cases, the A1 has a lower delta TC than the T1 combination. And last but not least, the manufactured waste shingles versus the tear-off shingles. What you see here is that the delta TC values are the same, but what's different is that the tear-off shingles requires a higher dosage, which I think we would expect because they're stiffer. They're providing a stiffer binder. All right, this is a little bit hard to see, but what we did is we looked at our binder blends. We have complete blending, right? When we take our extracted and recovered recycled binder, our virgin binder, and our recycling agent, we mix it well, right? Which is not what's happening in the mix. So we recognize that, and so we did something called the Mortar procedure, which is a draft standard right now for AASHTO that they've been working on through the ARC at UNR. And so we did the Mortar procedure, which basically just gives you a much more realistic way of not, you're still using the DSR and the BBR, but you're not having to extract and recover the binder. So it's much better in that case in terms of the realistic blending and also the time and effort involved. So what we see here is these are the 3 Nevada blends. So this is the control Nevada blend. This is with the tall oil. No, this is with the aromatic extract. This is with the tall oil. And this is the Texas blend, and then control blend, and then this is with the recycling agent, with the tall oil recycling agent. And what you're looking at here is that the solid colored dot is what the binder grade, the high temperature binder grade you get from the binders where you have complete blending. And this open circle is what you get from the Mortar experiment when you don't have the complete blending, the more realistic blending. And so what you see, number one, is there's a bigger gap between the binder and the Mortar at higher high temperatures, and that's true for low temperatures as well. This one they're verifying this because this is not what we would expect. In all cases, in general, except for this one, the binder is higher than the Mortar. So the binder, the complete blending, is sort of overestimating the high temperature grade, which I believe is the case. So the Mortar is a little bit more realistic. You also, so this gap is bigger over here. For the low temperatures, again, when the low temperature is lower, there's this bigger gap between the Mortar and the binder results. And these differences are anywhere between 3 and 6 degrees Celsius. Okay, so a half to a full grade, if you will. Of course, we need to look at the continuous grade as well. Okay, and then the last thing we've done is we've tried to validate what's going on in terms of stiffness and cracking resistance, because I feel like that's the ultimate test. So what we have here is some resilient modulus results. What you see is the green this is the cores at construction in solid, and then on top this is the cores at 1 year. So the stiffness is definitely getting greater with actual field aging. And then what you see in the blue is this is the lab mix, lab compacted specimens after short-term oven aging. with some protocols that we originally developed in 949, and then we verified them in 952 with 40 more mixtures, and then we verified it in this project. Do these still hold for with recycling agents? And we feel that they do. So this is short-term oven aging, and then after long-term oven aging, 5 days at 85°C, of course, they're stiffening. Okay, so that's number one thing you see. This is the virgin mix with nothing in it. This is the control with the recycled materials but no recycling agent. Okay, so they're stiffer. That makes sense. This is the recycled mix with the recycling agent at the field dose. And you see that at that low 2.7% dosage, there's not a whole lot of change, maybe a little bit more so with the cores. You also see here that the cores at 1 year are stiffer than the long-term oven-aged 5 days at 85°C. That's something that we also found in 952, that 5 days at 85°C is not doing 5 to 7 years of aging. It's doing maybe 1 year in 6 months, maybe in a warmer climate, and maybe 1 to 2 years in a colder climate. I think I'm quoting that right. Okay, so what happens if we took that mix, this one right here with the T1, and we actually did it at the optimum dosage, so the 4.5% that we would find from those graphs. Well, now this looks a lot. It did go down compared to the control, as we would expect. So this is kind of verifying our recycling agent dosage selection method. This is what happens if you go to the 64 minus 28. So the 64 minus 28 compared to the control goes way down compared to the one that just had the field dosage of T1. So this is the 64 minus 22 with T1, and this is what happens if you change that virgin binder grade. So that, again, has a big, big impact. This is what happens if you use the A1 recycling agent at the optimum dosage. So this kind of shows also that the T1 at the optimum dosage, which I think is 4.5, and the A1 at the optimum dosage, which is like 6. Remember, it took a little bit more. But it still does a pretty good job of restoring you back to, at least partially, to the virgin mix. And that's true but at both short-term oven aging and long-term oven aging. This last one is, obviously we're kind of in the middle of doing this one, but this is with the tall oil and now switching out to the tear-off shingles instead of the manufactured waste shingles. So this one would be compared to this one. So yeah, it's about the same as long as you're using that optimum dosage. So basically sort of all three of these kind of verified our dosage selection method. And here's some preliminary results from the fatigue cracking results. So what we have here is this is the virgin mix with nothing in it. We put in the recycled materials, and we do bump the grade of the binder down to a 64 minus 22, and we get the green. It's like, whoa, that just changed a lot, right? The slope of this fatigue curve changed a lot from green to blue. Then we put the recycling agent in at the field dosage, which we know is not completely as much as we would like, and it definitely has a big effect in sort of partially restoring that cracking resistance. So the next step, as I mentioned, is trying to look at this, what happens with the recycling agent with time, with aging. That's pretty important. We're looking at binder compatibility. We're actually going to send some blends to WRI to do that SARA-AD analysis. We're going to send them at the optimum dosage by this method. We also were looking at a sort of a faster compatibility test, which is called the exudation droplet test, where you have the material on a marble slab and you see how much the marble absorbs. Just trying to do something more practical than send your blend to WRI for X amount of money. But we want to understand the differences and how that works together. Then, of course, I feel like the main proof is in the mixture cracking test. So we're finishing up some SCB testing. We've been looking at a comparison of the Illinois and the Louisiana method. I think we're moving on with the Illinois method. And we also are trying to get the equipment up and running at UNR to do the low temperature cracking. So we're looking at cracking from a variety of different standpoints. We're also doing the layered elastic analysis with the VECD results to try to look at the actual pavement structures that are in the field and tie back to the field projects. And then, of course, hopefully we're going to get a couple more field projects, probably in Missouri, maybe finishing up in Florida. We may end up with more than we can do, but we'll get it done because phase 3 is all about validating some of the tools that we've come up with for binder and mixture testing, as well as this dosage selection method.